Welcome to coinSense. Disclaimer: this video is for informational purposes only and shall not be construed as financial, investment, legal, or tax advice. The sender holds positions in the digital assets mentioned, and shall not be held liable for any errors, omissions, or actions taken based on the information provided herein. Do your own research. Avalanche Platform Whitepaper, the paper outlining the architecture of the Avalanche platform and the various features that make it unique. 5. Discussion: 5.1 Optimizations. Pruning. Many blockchain platforms, especially those implementing Nakamoto consensus such as Bitcoin, suffer from perpetual state growth. This is because, by protocol, they have to store the entire history of transactions. However, in order for a blockchain to grow sustainably, it must be able to prune old history. This is especially important for blockchains that support high performance, such as Avalanche. Pruning is simple in the Snow family. Unlike in Bitcoin and similar protocols, where pruning is not possible per the algorithmic requirements, in $AVAX nodes do not need to maintain parts of the DAG that are deep and highly committed. These nodes do not need to prove any past history to new bootstrapping nodes, and therefore simply have to store active state, i.e. the current balances, as well as uncommitted transactions. Client types: Avalanche can support 3 different types of clients: Archival, Full, and Light. Archival nodes store the entire history of the $AVAX subnet, the staking subnet, and the Smartcontract subnet, all the way to Genesis, meaning that these nodes serve as bootstrapping nodes for new incoming nodes. Additionally, these nodes may store the full history of other subnets for which they choose to be validators. Archival nodes are typically machines with high storage capabilities that are paid by other nodes when downloading old state. Full nodes, on the other hand, participate in validation, but instead of storing all history, they simply store the active state, for example current UXO set. Finally, for those that simply need to interact securely with the network using the most minimal amount of resources, Avalanche supports Light clients which can prove that some transaction has been committed without needing to download or synchronize history. Light clients engage in the repeated sampling phase of the protocol to ensure safe commitment and network-wide consensus. Therefore, Light clients in Avalanche provide the same security guarantees as full nodes. Sharding. Sharding is the process of partitioning various system resources in order to increase performance and reduce load. There are various types of sharding mechanisms. In network sharding, the set of participants is divided into separate subnetworks to reduce algorithmic load. In state sharding, participants agree on storing and maintaining only specific subparts of the entire global state. Lastly, in transaction sharding, participants agree to separate the processing of incoming transactions. In Avalanche Borealis, the first form of sharding exists through the subnetwork's functionality. For example, one may launch a gold subnet and another real estate subnet. These two subnets can exist entirely in parallel. The subnets interact only when a user wishes to buy real estate contracts using their gold holdings, at which point Avalanche will enable an atomic swap between the two subnets. 5.2 concerns post-quantum cryptography. Post-quantum cryptography has recently gained widespread attention due to the advances in the development of quantum computers and algorithms. The concern with quantum computers is that they can break some of the currently deployed cryptographic protocols, specifically digital signatures. The Avalanche network model enables any number of VMs, so it supports a quantum-resistant virtual machine with a suitable digital signature mechanism. We anticipate several types of digital signature schemes to be deployed, including quantum-resistant RLWE-based signatures. The consensus mechanism does not assume any kind of heavy crypto for its core operation. Given this design, it is straightforward to extend the system with a new virtual machine that provides quantum-secure cryptographic primitives. Realistic adversaries. The Avalanche paper provides very strong guarantees in the presence of a powerful and hostile adversary, known as a round adaptive adversary in the full point-to-point model. In other terms, the adversary has full access to the state of every single correct node at all times, knows the random choices of all correct nodes, as well as can update its own state at any time, before and after the correct node has the chance to update its own state. Effectively, this adversary is all-powerful, except for the ability to directly update the state of a correct node or modify the communication between correct nodes. Nonetheless, in reality, such an adversary is purely theoretical since practical implementations of the strongest possible adversary are limited to statistical approximations of the network state. Therefore, in practice, we expect worst-case scenario attacks to be difficult to deploy. Inclusion inequality. A common problem in permissionless currencies is that of the rich getting richer. This is a valid concern, since a POS system that is improperly implemented may in fact allow wealth generation to be disproportionately attributed to the already large holders of stake in the system. A simple example is that of leader-based consensus protocols, wherein a subcommittee or a designated leader collects all the rewards during its operation, and where the probability of being chosen to collect rewards is proportional to the stake, accruing strong reward compounding effects. Further, in systems such as Bitcoin, there is a big get bigger phenomenon where the big miners enjoy a premium over smaller ones in terms of fewer orphans and less lost work. In contrast, Avalanche employs an egalitarian distribution of minting. Every single participant in the staking protocol is rewarded equitably and proportionally based on stake. By enabling very large numbers of people to participate firsthand in staking, Avalanche can accommodate millions of people to participate equally in staking. The minimum amount required to participate in the protocol will be up for governance, but it will be initialized to a low value to encourage wide participation. This also implies that delegation is not required to participate with a small allocation. 6. Conclusion. In this paper, we discuss the architecture of the Avalanche platform. Compared to other platforms today, which either run classical-style consensus protocols and therefore are inherently non-scalable, or make usage of Nakamoto-style consensus that is inefficient and imposes high operating costs, the Avalanche is lightweight, fast, scalable, secure, and efficient. The native token, which serves for securing the network and paying for various infrastructural costs, is simple and backwards compatible. $AVAX has capacity beyond other proposals to achieve higher levels of decentralization, resist attacks, and scale to millions of nodes without any quorum or committee election, and hence without imposing any limits to participation. Besides the consensus engine, Avalanche innovates up the stack, and introduces simple but important ideas in transaction management, governance, and a slew of other components not available in other platforms. Each participant in the protocol will have a voice in influencing how the protocol evolves at all times, made possible by a powerful governance mechanism. Avalanche supports high customizability, allowing nearly instant plug and play with existing blockchains. Please subscribe, like, and share if you enjoyed this video. Thank you for your time.